I review paper, what are the research going on in memory sum. There are focusing on different kind of memory sum. I have already uploaded the lecture, so I'll just go through it now.
That's not part of our. Yeah. I have another question. Is Dr. Kevin here? Like, I couldn't.
Kevin?
Dr. Kevin Patrick?
I'm not sure whether he's at this moment not, or whether he's in his room or not.
Okay.
But I saw him at 3 p.m.
Because you went, I think Dr. Kevin also went. I don't know. It feels like nobody was. The last week Saturday, yeah. So I was sending mail to you, Dr. Masood Chaudhary, and also Dr. Kevin. Nobody was.
Answered.
No. So.
Because Masood Chaudhary was also traveling.
Yes, I think.
He has some conference or something else. I was traveling.
I thought.
I'm not sure about Kevin.
I thought all of you went to some conference. I think maybe they went. Okay. That was my assumption. Sorry.
But I'm not sure about Kevin. This topic is related about some flexible memory technologies. So we already discussed about the memories, right? The ROM, RAM, the SRAM, DRAM, flash memories. But today this is very advanced technologies. We are now focusing on different kind of flexible things like an watch, like monitoring cell, because doctor can give you some monitoring. So they mentioned some what type of watch, not a fitness watch. So in those cases you have to collect the data and store the data. So this is a flexible memory technology. So there are some challenges. We need to choose the materials as well. How we can choose the materials, how we can fabricate those things. This is all about these things from review paper. So materials of flexible memory. So here we talk about the types of memory, flexible memory introduction, materials for flexible memory cells, and one type of memory cell is known as real-time RAM and applications. We already know the types of memory, right? One is volatile and another is non-volatile. This is a very general one. So this also goes for the flexible memory. The volatile one is it can store data temporarily. When the power is gone, the memory will also gone. But it is the advantage is quick access to the data or information, data loss upon the removal of power. On the other hand, for the non-volatile case, retains data without power but slower write and erase speeds. These are some advantages and disadvantages of those memories. The same thing used for, so you can mention that the volatile memory used for the fast memory access when power is removed, that is lost, and non-volatile memory is memory that holds data even when power is removed. So this is the very basic one, DRAM. We already talked about it. It's just a capacitor and a MOS transistor. When the MOS transistor, when the capacitor will charge, then we can say the store 1, and when there is no charges, we can say store logic 0. The very basic one. It consists of a transistor and a capacitor. But if you want to design these flexible memories, we have to have some requirements. The first one is material. The basis it's supposed to be flexible. A flexible material. The substrate itself should be flexible. Then we can make a flexible device, a flexible, for example, it's a memory cell, it can be a watch, it can be a monitors. Inside the monitor, for example, it's a medical device. Inside the monitor, you can have a structure so that we can store the data even. The camera even, a flexible camera can come in future, so where they can store. So whenever the device is flexible, it's not only the some part of the portion of the device will become flexible. We are focusing on how we can make every parts, make it flexible. For example, the display, the battery, the circuit, the transistors, and even the memory. So everything, because whenever we have a system, in the system we have 5 important parts. One is the control system, another is the battery or the power system, and the third one is the memory, so to store the data. Fourth one is the communication, that means an antenna, so that we can communicate for in and out devices. And another one is the display. These are the 5 important things in the electronic circuit. Everywhere you will have to have these things. So requirements is the material flexibility, then the data retention, and the energy efficient of the low power. Of course, whenever we focus on designing any electronic circuit, we have to focus this one, energy efficiency, the low power consumption. Otherwise, if it is a high power consumption, it requires more battery, it requires more current, electricity cost will be increased, then heat generate will be there. If heat generated, then it will be affected our transistors, because all of the electronic circuit based on the semiconductor material. So this low power is important. There are a few different types of flexible memory. One is known as FRAM, that is ferroelectric random access memory. We already know what is random access memory, but this random access memory is based on the material they use is a ferroelectric material. So that's why it is known as FRAM. Here how it works? It works switching states defined through the direction of polarization. So why there will be some capacitance will be formed. So in the capacitance there will be polarization, the positive charges and the negative charges. So the current will flow either in the higher direction or the lower direction. Depending on the direction or depending on the polarization, we can say storing 0 or storing 1. Another one is known as RERAM. RERAM is the resistive random access memory. Today we will talk about the RERAM here. And we also have thin film transistor, thin layer of semiconductor, dielectric and conductive materials. Thin film transistor is a very narrow thin film transistor. The material, we call it 1D material. Sometimes it's a 1D material, means it has only one dimension. It has only the, for example, the length. There is no width, no thickness even. So this is a 1D material or 2D material, very thin film transistors. So as I mentioned, we have to have, as you already see that, whenever we try to design the RAM or ROM, it is all about the what? MOSFET, a field effect transistor, right? So whenever it is a field effect transistor, or then and the field effect transistor is a basic structure of a capacitor, a parallel plate capacitor. So it's a metal contact, then oxide layer, and then another metal layer. So there will be an upper layer, then the lower layer, and also the oxide layer. So the substrate foundation, as if we are talking about a flexible one, so it can be any polymer substrate. PET, paper, PET is a polymer substrate. PI, right? PI is a polymer substrate. PET is a polymer substrate. Then PDMS, all are polymer substrate. Polymer substrates are more flexible. Paper is also a polymer substrate. So polymeric substrate, or it can be a flexible glass.
Graphite?
If you buy fabricating technology, state-of-the-art fabricating technology, if you make a glass to the thickness of few nanometer, the glass itself will become flexible. Depends on the flexibility, how you can say this is flexible, by reducing its thickness. And it is possible now, we can reduce the thickness of glass into some few nanometer. And that glass can act like a flexible material. Yes.
Graphite can be a
Yeah, of course. Graphene. But anything, any material which can be make your thickness less than few nanometer, few millimeter, less than 1 millimeter, actually we can make it flexible. Okay. For example, now most of the cases when you have the PCB, right? PCB board, it is made from what? It's made from FR4 substrate or Rogers substrate. So usually they have the thickness of more than 2 millimeter. But now we have FR4 substrate which has only 5 millimeter, 0.5 millimeter, sorry. 0.5 millimeter. Then this FR4 is also can have a flexible substrate. Okay, so the thickness is important. Then the metal oxide, as I mentioned, oxide layer. So the oxide layer can be made of zinc oxide, titanium oxide, aluminum oxide. Any kind of oxide we can produce. And the metal of the conductive layer, on top layer, the conductive layer can be gold, Au, can be silver, Ag, aluminum, nickel, tungsten, or indium tin oxide. Most of the flexible display in our phone, the touch panel, are actually made of ITO, indium tin oxide. The indium tin oxide, because they are the cheapest one. The cheapest one, they are transparent one, because whenever if you want to make a display, the phone, you have to very clean, transparent, you can see. Otherwise, if it is not transparent, we cannot make the device, the monitor itself. So to make our phones, our tab, most of the cases we use ITO. But the ITO is a problem. ITO is very fragile. You cannot make a foldable phone. So the Samsung, they have done the foldable phone. They don't use the ITO. They use some other material that is very expensive. That's why Samsung phone, the foldable phone, is still very expensive, more than $1,200, right? More than $1,200, because the material they used is 2,000. $2,200. I'm sorry, I said 1,200. I was thinking to buy. I think it will reduce someday 1,000. So it will take long time. Okay. Anyway,
it was 12,000 to be honest.
Yeah,
at the point.
Because that's why no other company is still not focusing on that, because they are very expensive material they are using. But myself, interestingly, I have a patent. I have a patent of this material. I make ITO flexible. During my postdoc in Japan, I made ITO flexible. I have a patent. But still they are not using. Someday they will release and I will be rich people because I have a patent, 30% owner of that patent. So someday I believe that company, I work for Sumitomo Chemical. This is one of the largest chemical industry after DuPont. DuPont is a USA company and Sumitomo is from Japan. I work for them. I have a patent with them to make this ITO flexible. I make another layer on top of ITO so that it can make foldable. So anyway,
is it cheaper than the ITO?
Yeah, ITO is cheaper. ITO is cheaper. We just make it possible that we just show them if you do this there, if you put this there. I can say it now because I have a pattern already. So actually, what I have done, I first take the ITO, then with the laser I cut it. Because for example, this is the ITO. Then I cut it with laser, a diamond structure. I cut with a diamond structure like this with the laser.
On the top?
Yeah.
On the top?
On the top.
Okay.
On the top with the eraser, the laser cutting.
Okay.
So what does it mean actually? When I cut it, so that means it becomes insulating. ITO is a conducting element, right? All over the year. So this is ITO conducting. Whenever I cut, so this layer and this layer is now isolated. So it's not can work as a conducting layer, right? Then what I have done, I put a sputter a gold layer.
Okay.
Sputter a gold layer. Then when the gold layer is sputtered, then I watch that here it becomes whenever I cut, it's actually like a trench. It's actually like a trench. A very than 1 nanometer thickness. You cannot see in the open eye. You have to see it with the microscopic view. So 1 nanometer thickness. So the gold actually put into that 1 nanometer scale. So now what happened actually? Wherever actually we fold something, we actually give some pressure, right? Due to that pressure, that became crack. So what I have done, I make the crack first, then I put a conductive layer. Now whenever we are trying to fold it, they have some space to get that, hold the power or hold the strength. So now they are not bending, they are not cracking. The energy is going down whenever we fold it, and whenever we make it flexible, then it makes it again. So that's the technique I observed. So here also we tried different shape, interesting shape. We tried just a line shape. We tried a wave shape. We tried circle shape, different shape. Finally, this shape worked. And another interesting thing is that we tried to find out a plant, some natural plant. I don't forget the name. There are some plants which actually increase
Money
spirally.
plant?
Money plant in our country we call it money plant. Here I don't know what they said. Some plant you saw, they actually grow like spiral, like a spiral, the bending. So we try why they bending. What happened when they bending? Whenever we take this microscopic view for that plant, we found that their stem cell have this diamond structure. It's a natural one. So because the diamond structure, whenever you push the pressure, so they just take like this, so they can hold the load equally, and whenever they come hit, then the load is released. Whenever you pressure, they come like this way. Whenever you release, they come this way. So the same thing happening. So whenever we are trying to give the pressure here, so they will just increase the distance. Whenever you just increase the distance. So this is the thing I have done, and we already tried to make a phone size, so like a foldable phone, and the stretch actually have given in the hinge part. Whenever this is a foldable phone, you are giving the stretch only the hinge part, not whole part, right? So only, for example, 3 millimeter by 2 millimeter.
Is it visible, those gold that
No.
you put?
Because it is only 1 millimeter thickness. 1
Nanometer
nanometer.
thickness.
1 nanometer thickness only. You cannot see open eye.
Yeah, open eye, yeah.
I have one sample in my room of that sample I prepared. So you have to create only the hinge part. That's 3 millimeter by 1 millimeter. Other than that, you don't need. Then we prepared it, and we just asked the company, because they also work with Samsung iPhone. So we just asked them how many days people use one phone. According to their statistics, people used to have their phone for 2 years. Then they try to change the phone, and in 2 years they can fold the phone 200,000 times, maybe. In total, 200,000 times. So we just test for 200,000 times, and it takes 2 days for us to test. We just started a machine, and we go back home. Then it just keep
Counting?
200,000 times. Still, after 200,000 times, the resistance growth is only 5 ohm.
Oh, the
5 square meter. The resistance, because when we have an insulating layer, that means the resistance growing, right?
Yeah.
So the resistance will grow, but it still is only 5 ohm per centimeter square.
But by folding, the resistance also grow?
Yeah.
So
At the very beginning, resistance is 0.
Yeah.
Full conductive layer. Now you start folding.
yeah.
Resistance will grow.
Why?
But you have to limit, because the crack, due to the crack.
Oh.
So if it is a still ITO, single ITO, whenever you do crack, we tried with the single ITO, it was just after 10 times folding, it's reached to mega ohm, 1 mega ohm. That means it is just totally disconnected
Useless.
from this side to this side.
Useless. Oh, okay, got it.
So if you want to use, so if you have giving the positive here, right, negative here. So whole surface supposed to be conductive element. Otherwise, touch will not work.
Mm-hmm.
So if this portion is fragile here, this portion and this portion separated, then touch will not work.
Oh, gotcha.
So anyway, so this is the flexible things. We have to think about these metals. Yeah.
How do you place this, like on the electronic screen or something? Now
So here in the display, on the display, just after this part, then we have the layer of the
Touchscreen.
circuit, touch screen circuit. So capacitive touch screen circuit. But the layer itself is for example, maybe this is an ITO circuit. So whenever you try to fold it, if the ITO cracked here, then this touch will not work. So this is the major part.
back of it, we should not have any electronic circuit.
In the back also electronic circuit, they can use
That is
that
also
thin film
flexible.
transistor. That becomes also flexible.
I have one question. Why didn't you use tungsten, one of the most hardest,
Oh,
and
because
also the
expensive.
titanium?
Expensive.
Okay.
So
Gold is cheap.
So yeah, gold is also expensive, but depends on that. That's I'm coming to your answer. So this is a research. So whenever you go for research, you have to have some facilities condition. If in my lab, I have only gold target. If I don't have the gold target, instead of gold target, if I have aluminum target, I can use aluminum. If I have the silver target, I can use the silver target. So this depends on the facilities you have. For example, in our UMKC, maybe some chemistry research lab, they have the sputtering machine, but they should have some target. We call it target. On the target, we sputter the material or deposit the material onto a substrate.
Oh, that
The target.
device. Okay. Got it.
So in my lab, they just have the only gold target. That's why we use the gold. But gold is still expensive. We should use either aluminum or silver.
Silver. I don't know. Like if you want to make it robust, I was saying tungsten.
Yeah, you can use the tungsten, but the expensive.
Expensive.
Then types of switching mechanism. In case of the memory cell, we have two different kinds of switching. One is known as filament-based switching, another is known as electron-based switching. In the filament-based switching, it is ionic migration. That means ions will migrate. On the other hand, if it is an electron-based switch, the electrons will migrate. That means the electrons, the charge. So these are two different kind of switching mechanism. So in case of the filament-based, the switching speed is moderate to high, but if you use the electron-based, the switching speed is very high. Energy efficiency, the low power operation. On the other hand, if it is an electron-based, it is high energy requirement in some cases. Application ReRAM or CPRAM. On the other hand, the electron-based is flash, DRAM, and FRAM. What about the durability? Potential degradation of filaments and high endurance. Of course, the filament-based one is some challenges of this potential degradation with the filament. So this is a PRAM in greater detail. So RRAM, I'm sorry, because we talked about the both PROM, that's why. It's an RRAM. RRAM is register-based, a register-based RAM, a two-terminal device, and fundamentally works by changing the dielectric properties. Positive to negative, the polarization, changing the polarization. When applying a positive voltage, depending on the material, it will create an oxygen vacancies. Depending on material means, because we already know if it is a silicon-based, maybe it requires 0.7 volt. If it is a germanium-based, it requires 0.3 volt. So depending on the material, you have to apply some positive gate voltage, because you have to MOSFET, right? A positive gate voltage. And when enough of these vacancies are created in the oxide bulb, the RRAM cell will switch to a low resistance state. It means, at the very beginning, if I go to the next slide, look at this side. So this one, we have the upper layer, we have the oxide layer, the green is the oxide layer, we have the anode one, the blue color, and we have the another metal layer. So in the middle, in the oxide layer, at the very beginning, it can see it has no vacancies. That means no vacancies means there are no absence of electrons, so that electrons can pass. We know that in the semiconductor, when there is a vacancy, electron can pass. So there is no vacancy here. That means it is high resistance. High resistance means the current is not flowing. Now when you apply some voltages, that means programming, you want to write something, then off to on state, the vacancy is here, so electrons start to flow. And when you reach to the totally on state, that means it's a low resistance, from two metal path, we already have some path. It's like a channel. Channel is there now. We have a path from anode to cathode, so electron can pass. So this is known as on state. Again, if you want to erase, what we do? We just need to get back the electrons. So electrons again going away, far away, and the oxide layer is becoming again empty. So this is how we can work. So whenever there is no vacancy, we call it low resistive state, LRS. And when we have a high resistive, we call it high resistive HRS. So in the low resistive state, the resistance is low, the current is there. We can see a white line. That means there is a connection, a full current is passing through it. And in the high resistive state, HRS, there is a gap or there is a cut insulating between the anode and cathode. So here we mentioned this thing about these things. So when applying a positive voltage, depending on the material, it will create oxygen vacancies. And when enough of these vacancies are created in the oxide bulb, the RRAM cell will switch to a low resistance state, which can conduct current to flow. The low resistance state means that there is enough of a conducting filament to conduct the current. Thus, in a computing system, this can be interpreted as a logic 1. And in case of high resistive state, HRS means that isn't enough of a conducting filament to conduct current, so it will relate it to logic 0. So when there is a current, there is a logic 1. The current means there is a charges, there is charges, so it's a logic 1. When there is no charge, it's logic 0. So here HRS is a logic 0 and LRS is logic 1. So we have top electrode, we have bottom electrode. Top electrode can be Au, silver or aluminum, silver or gold. And bottom electrode can be nickel, tungsten and ITU. Okay. In the bottom electrode, examples typically more stable metals to avoid reaction to chemical or physical changes. As is a bottom layer, so it has to some other layer behind it. So some chemical reaction can take place. That's why we are supposed to choose that are reaction to avoid chemical reaction or physical damage. So this is the same for things. There are many types of non-volatile memories. As I mentioned, resistive random access. Yeah.
So can you go to the previous? So that is a MOSFET, right?
Yeah.
MOSFET is connected with that.
So this is the capacitance one.
Capacitance.
MOSFET will be there because this is the storage one. MOSFET will be there. Okay. So this is the same. We have a top electrode, then we have a metal oxide, then we have the bottom electrode. The whole thing is only micrometer to some nanometer ranges. The whole device size. Okay. And this is the top electrode, this is the bottom electrode, this is the metal oxide, and this is the conducting filament. That means when there is a filament, there is a channel, then there is a flow of current. That means the filament, we are creating the filament like a channel. In case of MOSFET, we actually create the channel, right? Something.
So we can close the channel too?
Yeah. So if you take the voltage, the channel will be removed. So this is the IV characteristics. So in the IV characteristics, we can set 4 different regions. So high state, the HRS region. HRS region is this one. So when we have 0 voltage. So high resistive state, that means no current. Then we keep increasing our voltage 0.1 volt, 0.2 volt. Then it is the transition period. Then it will go to the side state. Side state means from on to off to on. From off to on. Once we reach here, then we call it low resistive state. In the low resistive state, we have high current. Then again, when you want to erase, then it will come back to this one. If you look at here, when we choose at the low resistive state, we can even at very small voltage, we can conduct the current. Then again, it comes back to the reset button, that means erase button, then it will come back to again the high resistive state. So here the process is mentioning. So at first, in region 1, initially the device is in high resistive state where the current is low for applied voltage. So this corresponds to off. In the second process, second region, as the voltage increases in the positive direction, the set point is reached where the resistance switches to a low resistance state, and this transition is due to the formation of conductive filaments in the device, enabling higher current flow. The device is in now on state. On the third region, once the LRS, the current flow is high, even the lower voltage melting on state, the third level. See, the current is going. On the final stage or the region 4, during this negative voltage swing, the set point is reached where the device transition back to the high resistance state, and this occurs due to the dissolution or disruption of the conductive filaments, turning the device off again. So here you can see as a flexible memory cell, very tiny flexible memory cell. Of course, this is one cell. One cell can hold only 1 bit. So you have to make actually thousands of cells to hold all the data. So here it is also same. We have a column, we have the row, right? Column and row, word line and the bit line. So this is the row, and this is the column. So columns are AU and the rows are silver. So electrode and the back layer and the top layer. So this is how, and on the middle we have the oxide layer. So top electrode is the silver, metal oxide bilayer thing is the SNO2 is the middle layer, and the bottom electrode is gold. In middle we have another layer is known as tungsten ditelluride layer. This WTE layer, which one is WTE layer? You can see here WTE. This one, this portion is WTE layer. This layer provides mechanical flexibility and improved adhesion, allowing for crack-free surface during the bending cycles. Crack-free. This is the most important thing. Whenever we try to bend any devices, any electronic devices, The main thing is cracking. So we have to somehow restrict this cracking. So that's why they use tungsten ditelluride layer, which provides mechanical flexibility and improves the adhesion, allowing for crack-free surface during bending cycles. Okay, and the bottom electrode is gold. And how they fabricate? The fabrication involves RF magnetron sputtering for thin films and a high vacuum thermal evaporation for electrodes. They use one is the evaporation technique and is the sputtering technique. As I mentioned, I also use the sputtering technique. In my case, I have the gold who just sputter. How it works is a sputtering machine is a vacuum chamber. You have to take out all the vacuum, then you have to set the current and the time. Then on the target is just like this. For example, this is the target. This is the white one is target. This is your sample. You put this one and you close the door and turn it on for 30 seconds or 40 seconds, depending on your time. We can control the thickness of the layer. That the layer will be on top of this substrate. So this is known as sputtering. And another one is known as evaporation. In the evaporation technique, the substrate, the substrate will be up on top, that it will evaporate from your target. So this is one of the examples from the reference paper. They just designed a flexible memory cell, a tiny flexible memory cell. So this whole part is actually the small part. The small part is this. So as I mentioned, the applications, the smartwatches, fitness devices, flexible display, medical devices like wearable or implantable devices. For example, if you want to design any for medical equipment, if you want to put into our body and you want to store the data for a week, the doctor wants to store the data for a week, you have to have a memory cell as well. For example, for a diabetes patient. So we have to know, doctor want to know for 7 days. And for after meal, before meal, at morning, at evening. So we need to store those data. So we can use this flexible memory cell, implantable memory cell. Another advantages of RAM are low power consumption, longer endurance, higher scalability, and better fit for flexible electronics. So these are the healthcare monitoring, these flexible devices, heart rate monitoring, blood pressure sensors, pacemaker, flexible display, pacemaker, and also the solar cell. Current and future application, high-speed, low-power embedded memory, nanoscale devices, neuromorphic computations, and artificial intelligence, AI. Because we are focusing on trying to make a robot, right? So the robot, if you want to design a robot, you have to also the neurons. So you have to also get memory. And Wahoo the memory, he knows better because he's working on machine learning. So you have to put millions of data so that the machine can also take decision, right? Millions, as much as you can give the data, then it can give you more accurate information, right? So that's why the information, personal information is very important. Nowadays, people also send personal information, right? This is very important because when the data center get the personal information, they actually try to develop their machines so that they can get more information. If you, for example, when we talk about things and after going back, today, maybe most of your phone will give you the advertisement about this memory cell today because we talk a lot about the memory cell, right? Once you go back, today maybe you'll get a Samsung foldable phone in your phone. The advertisement is to come.
This will definitely come.
Definitely come.
Always happens with
all of your phone. After this class, you'll see the advertisement is coming about the Samsung or something display or something mobile phone. So this is AI. So this is AI. They are giving informations. They just focus. Even you just scroll. You just see the monitor how much you are seeing at that particular news or at that particular applications or at that particular advertisement for 5 seconds, for 10 seconds, they just track that things. And then the same videos, same news will start to come in your monitor.
Google,
it's horrible.
In Google, they have many terms. In that many terms, there is a clause like we take your data information when you make the Gmail account.
So there is no privacy at all in this one. You are tracking every time, every moment. If anyone want to track you, they can. It's true. So anyway, so that's why actually sometimes I don't like this artificial intelligence. Really. There is no privacy. So this is the design of the requirement. What does the requirement for designing a flexible memory cell? Of course, flexibility. Your device itself supposed to be very flexible. Then the durability. Durability in terms of both the materials as well as your memory. The memory should retain there, right? And as well as your device should be useful for at least 2 years or 3 years, something like that. Scalability, that means how much you can production, because the commercial, when they use for think about the commercialization, the scalability is important. How much products you can prepare at a time, the fabrication time. Uniformity and the efficiency. We'll see one by one. So flexibility, the RRAM's operation depends a lot on what materials are used. It is totally depend on the materials because this is related to resisting. So different materials have different conductivity. So if you have the better conductivity material, then it will be fast, more fast, okay? Designers must choose materials that can withstand and stretching forces without interfering the functionality. As well as, of course, it's supposed to be very flexible so that our functionality will not disrupt. If the material's electrical properties are robust, but it's too rigid, it can't be a flexible, but because it is a conductivity is very good, but it is a rigid. We cannot make a flexible device. On the other hand, if the material is flexible, but not that good amount of electrical properties are too susceptible to changing from external forces, then they can be used as flexible computing. So we have to have both. Durability, as I mentioned, both in case of materials and data. In case of data perspective, from a data point of view, durability matters since memory is useless without data retention. And data retention assures that data will remain intact for a period of time. For example, if you are using any doctor using for 1 week information, so we should make sure that that data will remain for at least 1 week there. Otherwise, it's no meaning. In case of material perspective, from a materials point of view, durability is also important. We would want to use materials that can not only be flexible but continue to be used for operation over time, for a long time. Scalability is important as memory is notable dense circuitry. Most of the flexible devices out there are small and operate in low power. In context of flexible operations applications, we need to scale memory cells small enough to fit an array of memory cells in flexible device. So that means if you are thinking about this fitness device, this is a very small area. Here we have to have the sensors, you have to have the monitors, you have to have the controller device. Then we have to have the memory cell. So each part should be very narrow scale. So this scale is very important. So in context of flexible applications, we need to scale memory cells small enough to fit an array of memory cells. Okay. So fortunately, the RRAM can naturally start to the nanometer level. Uniformity. One of the greatest challenges for RRAM technology is ensuring uniformity. Switching between RLRs and HRS. So whenever we are switching 0 and 1, that means cycle to cycle. That means the resistance value during the repeated switching cycles may not be perfectly consistent, leading to a variability in the switching behavior. So whenever we are switching from 0 to 1000 times, sometimes it's not possible, cycle to cycle, sometimes this resistance value during this repeated switching may not perfectly consistent. And if it is not consistent, then it is dependent on the current, right? When the resistance value is not consistent, so for very narrow scale, because we are talking about 0.2 or 0.3 millimeters, something like that, right? So if there is a small change, instead of logic 1, it can give you logic 0. So this is one of the challenge, uniformity of the resistive value from cycle to cycle and also from device to device. So this D to D variability seems from imperfection in the fabrication process. That means during the fabrication, we have to make sure that all the cells are fabricated properly. The gap are uniform. For example, I have this one and I have this one. In this case, the gap is 0.1 nanometer, but in this case, it's 0.11 nanometer. That 0.01 is also effective because we are already action doing on only 0.1 nanometer. So this is the very important. So this is a fabrication process leading to the variation in filament geometry, gap distance, and other factors that affect switching behavior. Several factors can contribute to C2C variability. For example, the variation in filament formation. In some RAM device, the switching mechanism involves the formation of conductive filament. The size, position, number of filaments can vary between cycles, leading to C2C variation in LRH to HRS. Material properties. Variation in the material properties of the device can also affect the resistance level. As I mentioned, material to material, the conductivity is different. So this is another parameter. The third one is the device fabrication. Non-uniformities in the device fabrication process such as variation in the film thickness or electrode surface roughness can lead to CTC. That means whenever we are trying to device fabrication, as for example as a sputtering machine, if you sputter for one film for 10 seconds, another for 12 seconds, then the film thickness will change. And when the thickness will change, then it will not consistent. The resistive value will not consistent. This is a very simple one, very basic one. The roughness, because whenever we try to make an N-type and P-type, there is so many processes. We call it a lithography technique. In the lithography technique, we have actually 9 different steps. There is etching process, there is a masking process, and due to that, maybe some of the area, not whole area, some of the area can get roughness. So they are not flat. They are not homogeneous throughout the surface. That can also lead C2C variation. So having memory cells as uniform and consistent as possible is crucial for reliable memory operation. Efficiency. Since most devices are small and demands low power, that demand extends to memory, right? They are supposed to be very low, small as well as very low power consumption. So memory tends to use a significant portion of the design's power. Memory cell actually take one of these major portion of the power. We need the memory to minimize leakage current that affects from traditional memory architecture such as DRAM. We already know the MOSFET, the memory cell is made of what? MOSFET. In the MOSFET, we already know that there is no gate current, right? Because the insulator layer is there. But there is some current can be possible, which is known as leakage current. If you look at the MOSFET structure, the MOSFET structure is something like this. Right? This is the oxide layer. And due to this oxide layer is an insulator, we just mentioned that there is no current. The gate current is 0. But due to this fabrication problem or some other problems, a current can flow here or a point flow here. So charges should flow from here to here, but some charges can trap here. So if some charges trapped here, we lose charges. If we lose charges, actually we are losing current. So when there is a variation in current, instead of logic 1, it can become a logic 0. So this one, we need to memory to minimize this leakage current that affects more traditional memory architecture such as DRAM. Signal integrity. Beyond 10 nanometer density circuit, so in case of RAM, it is actually beyond 10 nanometer. So very tiny. And you have to make an array of those. So become more sensitive to certain coupling and parasitic effects such as cluster. So whenever we are trying to design this memory cell, this is not only a particular one cell, this is an array. And this array is actually only 10 nanometer. So when it is a 10 nanometer, can you imagine how dense they are? So whenever we try to write something, that means we are giving some voltage. If this voltage is much more than required, then it can create a crosstalk. A crosstalk means the voltage that we apply, the heat it is generating, it can affect its adjacent cell. Because they are actually like this, they are very close. Actually less than that, right? We can see in open eyes, it's nanoscale. So whenever you try to write 1 here, you are giving voltage and it will generate heat, and this heat can affect this adjacent cell. So this is known as crosstalk. So that I mentioned here. So beyond 10 nanometer density circuit, namely RAM, becomes more sensitive to certain coupling and parasitic effects. Coupling and parasitic effects such as crosstalk, IR drop, and sneak turns. Voltage drop indicates resistance, which is the critical parameter of the operation of RAM. Crosstalk is a phenomenon in transmission lines where a circuit is distributing another nearby circuit by proximity. And sneak pulses are general unintended electrical pulse. So this one is the crosstalk. So in memory device, thermal crosstalk refers to the unwanted heating of neighboring cells due to the heat generated by a cell during its write operation. So it seems that they are far away. Actually, they have only few point nanometer difference between this cell to this cell actually. So they are close enough. And due to that, this can lead towards resistance degradation of adjacent cell, affecting data storage and device reliability, especially in dense memory areas. This is known as crosstalk or parasitic. So how the heat generated during write operation memory cell, particularly in technology like RAM and phase change memory, generate heat. And this heat can propagate to neighboring cell, causing an increase in their temperature. This thermal crosstalk can lead to several detrimental effects like resistance degradation. The increased temperature in neighboring cells can cause a change in their resistance, potentially leading to incorrect data storage, as I mentioned. It's supposed to be store logic 0, now it's logic 1. Or it's supposed to be logic 1, it's now logic 0. Switching behavior. Thermal crosstalk can affect the switching behavior of the memory cell, making them more susceptible to errors. And retention performance, the heat can also degrade the device ability to retain the stored data over time. Data storage state failure. In extreme cases, the thermal crosstalk can cause adjacent cell to fail to retain the data they were intended to store. So this is very important challenge, the very sensitive challenge, we can say, the crosstalk. Impact of scaling. As memory devices are scaled down to higher densities, the effect of thermal crosstalks become more pronounced and challenging, right? Because nowadays we are trying to increase the memory. That means they are becoming more dense, and more dense. So this crosstalk becomes more pronounced and challenging. How we can mitigate? Researchers are actively exploring various techniques to mitigate thermal crosstalk, including optimized material section. That means we should choose some material that have very high thermal conductivity. So it can hold very high resistive thermal conductivity and heat dissipation properties. Array architecture, designing memory array with larger spacing between cells to minimize heat transfer. And also the cooling system, implementing cooling mechanism to dissipate heat and reduce the temperature on the memory array. So this is the one of the research paper they mentioned. So by increasing the spacing between the memory array, they can reduce the temperature. So for example, here we can see 180 degree temperature, right? But if you reduce that, if you increase the gap, if you spacing distance, this temperature can come down to below 30. But again, if you increase the space, it will take more pieces. So you have to trade off between this temperature and this space. And this is the crosstalking. So if you want to bias this voltage, this can lead. We are trying to bias these voltages, right, with 1 volt to store 1 writing, but it can lead to some other area. What is voltage drop? This IR versus offsets. In memory device, IR drops refer to the voltage drop across the resistance of the interconnects as current flow. Because whenever we want to write, right? So that means we have to burn out the filament. That means the current will flow. And when there is a current flow, the resistors are there, so voltage will drop. V equals to IR. It's an Ohm's law, simple Ohm's law. So in memory device, IR drops refers to the voltage drop across the resistance of the interconnects as a current flow through them, leading to non-uniform voltage and current distribution. This phenomenon is more pronounced in crossbar array. So in the crossbar array, this resistive RAM, where some cells are further from the reed circuit experiencing more resistance. If you go further away, it will have more resistance. Cell indices can be used to track the location. This is known as cell indices. So by the cell indices, we can track the location so that we can try to minimize the problem, or we can try to retain that data. So cell indices can be used to track the location of cell within the array, which helps in understanding and mitigating the effects of ion drop. So IR drop, as I mentioned, is derived from this simple Ohm's law. G equals to IR is the voltage difference between 2 points in a circuit due to the resistance of the conducting wire and the current flowing through it. In memory device, particularly those with crossbar architecture, this means that the voltage at a cell may be different from the intended voltage due to the resistance of the wires connecting to it. So we are supposed to give some voltage, for example 1 volt, but due to the resistance variation, it can be more than that, 1.5 volt, or it can be less than that, 0.7 volt. V equals to IR. So as R changes, so voltage drop will change. So that's the problem. So non-uniform voltage and current distribution, IR drop leads to variation in voltage across different cells, which can make it difficult to reliably read or write to the memory. Impact on performance. Uneven current distribution can affect the overall performance of the memory device, potentially causing errors or slowing down the read-write operation. Scalability limitation, IR drop becomes more critical as the size of the memory array increases, making it challenging to scale up memory device. Because when they become more closer, so it will become more challenging. Cell indices. What is cell indices? Cell indices means row and column indices are used to identify the location, the cell, the affected cell. We need to identify the affected cell within the memory cell. By tracking the cell indices, designer can understand how the distance of a cell from the reed circuit affects the voltage and current is experienced. Then we can mitigate. At first, you need to know your problem. At first, you need to know your distance, the location. Then we can try to mitigate. How we can mitigate? Okay, this is the distance. This is the amount of resistance is growing. Now we need to reduce the distance of that, so that the resistance will decrease. Or we can try to increase the voltages. Somehow we can mitigate. So this information can be used to develop strategies for compensating or mitigating IR drop effects, such as adjusting the read-write voltages based on the cell location. Design modification. So there are different kind of mitigation technique. The first one is design modification. So once you find the indices, okay, now we have to modify the design. So optimizing the layout of the memory array, widening wires, and adding more metal layers can help reduce resistance and minimize IR drop. So V equals to IR. If you reduce the drop of if you can reduce the resistance, the voltage drop will reduce. So how you can reduce the voltage drop? If you increase the width or increase the by metal layer, by widening the wires, we can reduce the resistance. Power delivery network, PDN design. Designing a robust PDN that efficiently distributes power and ground across the memory array can help reduce IR drop. Compensation technique algorithm can be used. So AI can be used to calculate expected IR for each cell and adjust the read-write voltages accordingly. And finally, ECO, engineer change order optimization. In some cases, designers may move cells to location that minimize IR drops. So that means they now change the location even, okay, depending on the design. So these are the things, and I just draw this information from these references. So this is, as I mentioned, just I try to let you know what are the advancement in the memory cell nowadays. We are focusing on everyone is looking for flexible device, and a flexible device any electronic device have 5 important parts: the microcontroller, the display, the memory cell, the power, and the communication. So if you can make all these 4 components flexible, then we can make a complete flexible electronic circuit. So now we are trying to make those flexible electronics, but of course still they are very expensive because the fabrication technology, state-of-art fabrication technology is required, state-of-art materials is required. If you want to use a very expensive materials, then it will be more costly. It's not possible for commercialization, the costly devices. So these are the things. So the challenge is there. The research is still going on. There is funding, huge funding is ongoing. So that's how I want to just share with you this small information. Thank you. Do you have any questions regarding our syllabus, our exam, anything? So we have our exam on Tuesday, if I'm not wrong, right? Tuesday at evening from 5:30 or 5:45. I think 5:45. From 5:45. It is at room number RH 312, not here. It is Royal Hall 312. And it is a 2 hours exam. You have to answer 7 questions. I already give you the sample questions, so you can prepare from those questions, and the answer is already in my hand notes.
How many questions did you say it was?
You have to answer 7.
Out of
7
10.
questions?
You have to answer 7 questions. Each will have 5 marks, so 35 marks.
Out of 10.
Okay, and how many questions total?
Out of 10.
Okay.
You have uploaded a Word file in the lecture note. There is some calculation like capacity calculation, then there is resistive calculation for the PMOS. Do we need them?
Oh, last one. Only one. I have only one equivalent PMOS. Oh, you don't need that for the practice. That one we just make how we can calculate, but we don't need that one.
Like I was thinking how you're going to give the question regarding this. Like you need to give all the question, just calculate all the data, then just put it in the calculator, then get it. Like
If I give you the exact question, then what will be
what will be the meaning
of
of
this exam?
Would there be trick question or just based on?
No. You mean true false MCQ?
Yeah.
No true false, no MCQ. The question just I mentioned, that will be the question.
Okay, we just need to follow the lectures and the questions.
Yeah. For the numerical problems, there are some small numerical problems maybe you have to follow, but the big one you don't need to do that.
Okay, I'm ready. Please share the lectures and the questions with me.
Sorry.
What is this on Google?
Yeah, Google.
Yeah. Things are changing.
Do you have hands
Too much.
That go over the flip-flops, and the SR latch?
Yeah.
Okay.
There will be no.
So flip-flop as well as designing by the CMOS of things.
Because I'm looking for the handouts and I don't see the, where you talk about latches. So when it comes to the design SRD and JK flip-flop, it's in here? Okay.
SR, did you teach the, I forgot, did you teach the SR flip-flop latches? Those are,
I taught you the designing SF flip-flop, D flip-flop, JK flip-flop by CMOS. So we have the
CMOS.
circuit, then we have the equations, and according to two equations, for example, for example, Q bar dot clock plus S, right?
Oh,
Then we have
okay.
Q bar clock, then we have this PMOS, parallel PMOS.
Oh, yeah, I remember now. Yeah. I remember.
No derivation. If I don't ask the derivation, only have to know how to design the circuit. So for input and output impedance, if you want to get input and output impedance, how the circuit works, then you can easily see so you can easily calculate the size equation, right?
This is the one? We're talking about this one?
Yeah. So this is Q.
Sorry, it takes a time. More line, how we connect the SRAM.
Yeah, but here I also draw the S.
This is
the
my
JK
like.
flip flop. I can remember.
Yeah.
I designed the JK flip flop, D flip flop, right?
Yes, sir.
SR flip flop.
Yes, sir. But you haven't submitted it in the campus.
I didn't.
Yes.
Really? Let me
But
see.
I have the handles, so I will
Let me see my handles.
In which lecture? Like this in this lecture?
Let me see. If I don't upload, I should upload by now.
We have only 2 files on the name CMOS and CMOS 2.
Oh, in the CMOS, in the earlier lecture. Yeah, you think you.
That's cool, yeah, I've been just down with it.
All state
So I didn't upload that one. Okay, I will upload. Yeah, Cal, you are right. I didn't upload. I should upload that one too.
Okay,
I'm going back to my room. I'll upload.
all right, thank you.
Thank you.